In section 4.5, we deal mostly with isosceles triangles. Before I get to the definition and the rest of the lesson, a rare blank white page. I did this so that the word isosceles isn't anywhere on the screen. As soon as I flip to the next slide, you'll have 6 of them on the screen. Isosceles is one of the most commonly misspelled words that we will have this year in geometry. Fortunately, most math teachers won't care if your spelling is perfect as long as you are close. Most math teachers care if you get the concept, so conveying that is the important piece. Just get in the ballpark. Some of these are clearly pretty close. The top one is by far the most common way it is misspelled. And yes, I really did have a student try the bottom one on a test one time. That's not so close. But it was funny. However, my favorite misspelling actually comes from one of my all-time best geometry students who couldn't spell a lick. His spelling was atrocious, but he only missed 1 point all of the first semester. That could never have happened if spelling had counted. Back to the regular lesson. And look, just as I promised, the word isosceles appears 6 times on this page. And some of you have just paused to try to count if in fact there were 6 of them. With 6 of them on the screen, maybe the correct spelling will subliminally seep into you. Let's start off with the definition of an isosceles triangle. This is the definition with isosceles number 7 in there. An isosceles triangle is a triangle with at least 2 congruent sides. Students often are confused if equilateral triangles also count as isosceles, but the definition says at least 2 congruent sides, so yes, equilateral triangles do count. The legs of an isosceles triangle are the 2 congruent sides. By process of elimination, that leaves only one side left that could be the base. The base of an isosceles triangle is the side which is not a leg. He is the odd man out. The base is the third wheel in this relationship. This is going to come as a major shock, I am sure, but the base angles of a triangle are the 2 angles that are next to the base. The base angles are the 2 angles I have shown in the picture. The third angle is the odd man out, or the third wheel of the angles. Amazingly enough, third wheel doesn't show up in the definition though. The vertex angle of an isosceles triangle is the angle formed by the 2 legs. There is your isosceles triangle anatomy. First, the isosceles triangle theorem. It says that if we have 2 sides of a triangle congruent, then the angles opposite those sides are congruent. So here I have a triangle with 2 sides congruent. That would be isosceles. This theorem says that not only are those 2 sides congruent, but the angles opposite those sides are also congruent. Those would be the base angles. The base angles in an isosceles triangle are congruent. Then we move on to the converse. The converse of the isosceles triangle theorem says that if 2 angles of a triangle are congruent, then the sides opposite those angles are congruent. Here I have a triangle with 2 angles congruent. But the sides opposite those angles are also congruent. Those would be the legs of the isosceles triangle. One of the big issues comes from students trying to remember when they use isosceles triangle theorem and when they use the converse when they're trying to do a proof. With the isosceles triangle theorem, you start with the sides congruent, and then you conclude that the base angles are congruent. With the converse, you start with the base angles congruent, and you can conclude that the sides are congruent. If you start with the sides congruent, then you use the regular theorem. If you start with the angles congruent, then you use the converse. Here on the screen there are 4 different shaped and rotated isosceles triangles. You may have noticed that all isosceles triangles are symmetrical. They all have an axis of symmetry. Here they all are. Those poor isosceles triangles. They didn't hurt anyone. And we come along and chop them in half, like nothing. But now that we have those axes of symmetry drawn in, we can fold each of these triangles over its axis of symmetry, and it will all line up perfectly. There is a theorem in this section which says this. If a line bisects the vertex angle of an isosceles triangle, then the line is also the perpendicular bisector of the base. This is the same concept that each isosceles triangle has an axis of symmetry, just a different way to say it. When you draw in that axis of symmetry, you do bisect that vertex angle. With an axis of symmetry, every piece on one side of the axis has a matching and congruent piece on the other side. Or if you look at the theorem, it says that when you draw in that blue dotted line, you have drawn in the perpendicular bisector of the base. It doesn't matter which way you think about it, you get the same result. These angles are both 90 degrees, and these 2 line segments are congruent. If you like thinking about it as an axis of symmetry, great. If you like the theorem and want to think of it in terms of a perpendicular bisector, that's great too. Whatever works for you. You just need to get it down because you're going to be drawing that in a surprising amount this year. It is extremely common for a student to get stuck on a problem, and then I will come along and say something to the effect of, what do we often do to those poor isosceles triangles? And the floodgates will open, and they will know what to do because drawing in that line is the key to the problem. It's extremely common with isosceles triangles. We chop those poor suckers up. The concept of a corollary is also introduced in this section. A corollary is a theorem that can be proved easily using another theorem. But at its heart, it's just another theorem. There are 2 corollaries in this section. The first is the corollary to the isosceles triangle theorem. I'll go over what those corollaries say and mean on the next slide, but we don't need them for the discussion of what a corollary is. Since this theorem was listed as the corollary to the isosceles triangle theorem, I know that it comes directly out of, or can be easily proven by the isosceles triangle theorem. These two theorems are closely related. Similarly, there is a corollary to the converse of the isosceles triangle theorem, which tells me that it comes directly out of, or is easily proven by, the converse of the isosceles triangle theorem. That's what a corollary is. Now let's see what these corollaries actually say. First, some vocabulary you probably already know. An equilateral polygon is a polygon with all equal sides. An equiangular polygon is a polygon with all equal angles. The two corollaries use those terms. The first corollary says that all equilateral triangles are also equiangular. The second corollary says that all equiangular triangles are also equilateral. These corollaries are why you hardly ever hear the term equiangular. Since all equilateral triangles are also equiangular, and every equiangular triangle is also equilateral, you only need to use one term and you instantly know that both things are true. And it would be really awkward to say it is an equilateral equiangular triangle. That simply just doesn't roll off the tongue. So we only need to say one of them, and the other is automatically true. There is no way to confirm this, but I suspect they chose to use equilateral because it is easier to say than equiangular. That's why you always hear of equilateral triangles, and rarely about equiangular triangles. Last thing. This idea that every triangle that is equilateral is also equiangular, and that every equiangular triangle is also equilateral, only applies to triangles. It doesn't work for any other polygon. Think about quadrilaterals. A rhombus is an equilateral quadrilateral. Say that 10 times fast. But it is clearly not equiangular. Similarly, a rectangle is an equiangular quadrilateral, but it is clearly not equilateral, so it only works on triangles. It isn't true for any other polygon. A triangle is the only one where every equilateral triangle is also equiangular, and vice versa.